Okay, now we want to look at a typical induction motor torque speed characteristic curve. Okay, so as we can see from the graph, this is the induced torque and this is the speed, the mechanical speed. Okay, so this is the characteristic of the induction motor. Okay, so actually we want to start from here, where when the value of Nm, okay, so this is the Nm, this is the speed of rotor, so Nm. So when the Nsync or the Nm is equal to Nm, okay, okay, when the value of Nm is equivalent to the Nsync, so what happened actually is the slip become 0. Okay, the slip become 0. Okay, so when Nm is equal to 0, so the slip will be 1. Okay, so when moving is over here, so the Nm will be increased and the slip will be decreased. Okay, when we look at this direction, so when the speed become slower until 0, so the slip become more higher. Okay, so at the N0, Nm0, so the rotor speed is 0. So you can see the rotor is at the static condition, so it requires higher torque. Okay, so therefore the characteristic of the rotor, the induction motor is the starting torque is quite high. Okay, so this is 100% of the load. Okay, so we assume that the load is constant. Okay, so when the load the induced or the torque required of the load is lower than the starting, so then the rotor will increase. The rotor will start to rotate. So you can imagine, so if the required torque is over here, okay, so where the starting torque is less than the required torque. Okay, so at this point the motor will not move. Okay, so therefore the starting torque should be or must be higher than the required torque. Okay, so then the motor will start to increase, start to rotate until the maximum induced torque. Okay, or the other name of the Tmax is the pull out torque. Okay, so later on we will see the pull out torque. Okay, so at this point, the value of slip, okay, the value of slip is equal as x max. Okay, for sure the value of x is not the highest value. Okay, but it happens, so they call it as x max. It happens at the torque max. Okay, so then the motor will the torque will start to reduce until the maximum the required load. So this is the working condition. So the working condition over here. Okay, so this is the working condition. Okay. Okay, at the working condition, we can see that this part is linear. This part, the graph is linear. Okay, a bit linear. Okay, where the torque is linear to the speed. Okay. Okay, so I include a link video for more explanation. So kindly please go to the link and see the video, watch the video. Okay, this is the a bit extra about this. Okay, so once the rotor, okay, the rotor speed exceed the ensing, okay, once the rotor is move faster than the ensing, so the motor will become the generator. Okay, so from the generator we can generate some mechanical electrical power. Okay, and then when the rotor, so this one is n equal to 0. Okay, so when the rotor rotate at the different direction, so this is will become a it's a braking region. Okay, so this is not a continuous continuous graph. This is not a continuous graph. Okay, like okay, this is the characteristic. Okay, where for example if you want to buy a motor, so you can see the characteristic first. Okay, so then you will know your requirement. Okay, then we can see that the torque and power converted versus the motor speed. Okay, so this is the black one is same graph as before, and the red one is the power. So of course when there is no movement, okay, so the power is become 0. Okay, and this is the maximum, n equal to n sync. Okay, so this is the, okay, I can say it's a maximum speed. Okay, so this is the maximum torque, and we can see that the power conversion, the maximum power is not at the maximum torque. Okay, okay, now we want to see at the maximum pull out torque. So how to calculate and measure over there? So since the torque induced is equivalent to the power of air gap divided by the speed of angular velocity of sync, so the torque induced maximum occur when the PAG is a maximum. Okay, so it is like a relationship. Okay, T max proportional to the PAG max. Okay, something like that. Okay, so since the PAG is equal to the 3 times I 2 power of 2 and R2 over S, so the T induced maximum occur when the power consumed by the load resistor, okay, over here is at maximum. Okay, so you can see that normally the changes happen during the sleep. So this is the sleep. Okay, so when is the power supply to the R2 is at maximum. Okay, so this one we need to refer to the equivalent circuit. Okay, so to find the maximum value, okay, what we need to do actually is we must use the maximum power transfer theorem. Okay, in a situation where the angle of the load impedance is fixed, the maximum power transfer theorem states that maximum power transfer to the load resistor R2 over S will occur when the magnitude of that impedance, okay, magnitude of that impedance is equal to the magnitude of the source impedance. So that impedance is this, is equivalent to the source impedance. So other than that is called as a source impedance. Okay, so the source impedance is RTH plus JXTH plus JX2, and the Z load is R2 over S. Okay, so when power of air gap is at maximum, okay, so Z source equivalent to the Z load. Okay, so we want to make we take the magnitude, since they include the J and also J, so real and imaginary, so we take the magnitude, and then we can get, or before that we can say, we can rewrite R2 over S equal to RTH plus JXTH plus JX2. Okay, so still with this is including the phase. Okay, so we want to calculate or measure the magnitude. Okay, so we just take the magnitude. Okay, so we will get this equivalent equation. Okay, so then the pull out torque actually happen at the slip maximum. Okay, so when over here, so you can see from this happen when this is maximum. So the slip at the pull out torques. Okay, so you can see from the graph, so this is the slip max. Okay, the slip max. So how to calculate the slip max? Okay, so they click the slip by using this equation. Okay, so at the pull out torque, so the slip max is equivalent to the R2. Okay, divided by root RTH square plus XTH plus X2 square. Okay, and then we replace the value of S. Okay, so if you still remember the equation, okay, I go back to the equation. So we can see that over here they have S over here. Okay, so we replace the X max. So then it become a new equation. Okay, so we replace once we replace, we can get a new equation. Okay, so this is the torque at maximum. Okay, so thus the T max is independent of R2 and X max is proportional to the R2. Okay, this is important to know this one. Okay, so we can see over here. So the T max, okay, the T max is independent. Is not dependent. Okay, it's independent. T max is independent of R2. Okay, and then the S max, okay, is proportional to the R2. Okay, okay, this indicate when we want to change the characteristic. For example, we want to improve the things, the induction motor. So for example, we can try to increase the value of R2. So R2 increase, so X max will be increased. Okay, see, remember over here is S equal to 0 and this one is S equal to 1. So this is at the starting condition. For example, the original graph. Okay, so this is X max. Okay, this is X max. Okay, so once we increase the value of R2, for example, over here we can write R2 is more than R1. Okay, so bigger than R1. So once R2 is bigger than R2, so S max 2 also bigger than S max. Okay, so over here this is less and this is much higher. Okay, so however the torque is constant. Okay, the torque is constant, is not dependent on R2. Okay, whenever we change the value of R2, the torque is still the same. So therefore you can see over here, so the value of the value of torque is still the same. The only change is at the pull out torques, and also the pull out torque is the same, the maximum torque. However, the difference is the the value of x max, okay, x max 2. So this one R3 is much more higher than R2, so S max 3 higher the change, okay. So up to the R6, okay. So what change here is the starting condition, okay, the starting torque, okay, the starting torque will be changed when we change the value of R, okay. For example, you have load over here, okay, this is your load, and the characteristic of your induction motor is this one, okay, this is your characteristic. However, the motor will not move, so you need to do some changes, change the parameter of R, increase the value of R, and then you can get the second graph, okay, second graph. So now you can move the motor, okay, you can the motor can start will start to rotate.